Hey Thinksters, and welcome to today's video. I'm excited to share with you my journey through the Google FooBar challenge, and this is the sixth video in this series. And I don't know the challenge yet. This is just as a live coding session. I will just share my thought processes with you. Try to solve the Google problems live, so that you can see. So where do I struggle? I just want to share my the thought process of an experienced coder, if I deem to say, so that you may learn something out of it. So let's start with today's session. So in the Google coding session, you have this share, and now we can check so you can always type in help to get all the commands like cd, cat, delete, and so on, so we can delete some data. So this is for GDPR compliance, and we can give some feedback, and we can also type in status, and this gives us a visual representations of the level we have passed. Okay, you can see. So in the first two levels were relatively easy, so probably today's session will be a bit harder. So we are currently at level 3, and I have completed 66%, so 2 out of 3 steps. So if everything goes correctly today, we will finish level 3 and successfully. And yeah, I've already, so there's a link, a refer a friend link, which I have already used. I gave it to Thinkster. I did some Thinkster session to some Thinkster challenges to give the winner of the Thinkster challenge this link, this referral, to participate in the Google FooBar challenge as well. So you can always invite only one friend. Otherwise, I would love to invite all of you, but it's unfortunately not possible. Okay, so let's start with the session. So if you type in ls, you see that there are two files, the file journal.txt and start here.txt. So we start here. They tell us type request to request a challenge, type help for a list of commands. Okay, so we already typed help. We know about this, so let's type request and get our new challenge. Okay, so the challenge is, there are a lot of difficult things about being undercover as Commander Landa's personal assistant, but you have to say the personal spa and private hot cocoa bar are pretty awesome. Okay, so the new challenge is called Bomb Baby, and it's added to my home folder. I have 96 hours to solve, and you see here the counter. So I have like 3.5, actually 4 days to solve this session, but I plan to solve it in today's session, so it should be more than enough time. Okay, so I will just, as I go along, I will copy and paste some of the stuff so that I can use it later to, maybe I want to make a course out of it. So, okay. Good. So then let's type, let's see what is in my folder. Okay, we have the folder called Bomb Baby. So we cd into this folder, check the contents, and again we have some files, so we can submit our solution either in Java or in Python. And we have again readme and constraints file as usual. Okay, so let's first have a look at the solution we already have. Okay, so it's just nothing. Type solution here. So I will just use my own shell for the solution. Usually we have so that I can try things out, and so it's just a bit more convenient. And so we have this structure, your code, and let's see what we have to do. Cat readme. Okay, so it's quite something. Okay, so the challenge is Bomb Baby. You're so close to destroying the lamp chop doomsday device, you can taste it. But in order to do so, you need to deploy special self-replicating bombs designed for you by the brightest scientists on Bunny Planet. There are two types, match bombs and M, and fecular bombs. Okay, so we have two types, M and F. And the bombs, once released into the lamp chop's inner workings, will automatically deploy to all the strategic points you've identified and destroy them at the same time. Okay, but there's a few catches. First, the bombs self-replicate via one of two distinct processes. Every match bomb retrieves a sync unit from a fecular bomb. For every match bomb, a fecular bomb is created. Okay, so we have a sync unit from a fecular bomb. So the match receives it. Already indicates that there is some recursion going on, maybe. Every fecular bomb spontaneously creates a match bomb. For example, if you had 3 match bombs and 2 fecular bombs, they could either produce 3 match bombs and 5 fecular bombs, or 5 match bombs and 2 fecular bombs. Okay, so we always like we have, if you have 3 and 2, okay, so if you have like 3M and 2F, then they can produce like 5, 2. So it's like we can represent it as a tuple. So we simply add them together. The sum of them is the first match bomb, and then we use the fecular bomb. Or we can have 3, 5, right? So like one value, the one I underscore, is the sum of both, and the other one is the original value. So this is like the overall structure. Now this of course can go on probably. Let's go back. Maybe we first read everything. So if you had 3 match bombs and 2 fecular bombs, they could either produce 3 match bombs and 5 fecular bombs, so the sum of both, or 5 match bombs, the sum of both, and 2 fecular bombs. The replication process can be changed each cycle. Okay, so we have some cycles going on. Cycle, what does it mean? Probably we have something like yeah, so we have a discretization of the time. So if this is a time, then we have like some discretization into cycles. And second, you need to ensure that you have exactly the right number of match and fecular bombs to destroy the lamp chop device. So we need the same. Too few and the device might survive. Too many and you might overload the mass capacitors and create a singularity at the heart of the space station. Not good. And finally, you were only able to smuggle one of each type of bomb, one match, one fecular, aboard a ship when you arrived. So that's all you have to start with. Thus, it may be impossible to deploy the bombs to destroy the lamp chop, but that's not going to stop you from trying. Okay, so what's the thing I again have to read about this general idea. But in order to do so, we want to destroy the lamp chop doomsday device. But we need to deploy special self-replicating bombs designed for you by the brightest scientist. There are 2 types, so we have 2 bombs to destroy the thing. Yeah, so these are our bombs to destroy the lamp chop device. So we have match bombs and fecular bombs. And so once we release the bombs, they will automatically deploy to all the strategic points you've identified and destroy them at the same time. So we can destroy everything, but the catch is that they self-replicate. Every match bomb retrieves a sync unit from a fecular bomb. For every match bomb, a fecular bomb is created. Every fecular bomb spontaneously creates a match bomb, so they create each other. And we need to have exactly the right number of match and fecular bombs to destroy the device, okay? You were only able to smuggle one of each type of the bomb aboard the ship where you arrived, so that's all you have to start with. You need to know how many replication cycles or generations it will take to generate the correct amount of bombs to destroy the lamp chop. Write a function solution mf where m and f are the number of match and fecular bombs needed. Okay, so our solution file, let's see, our code solution, like this is, let's call it m and f. for example, yeah, or maybe let's just call it X and Y, where M and F are the number of match and fecular bombs needed. Return the fewest number of generations as a string that need to pass before you will have the exact number of bombs necessary to destroy the lamp job, or the string impossible if this can't be done. M and F will be string representations of positive integers no larger than 10 to the power of 50. Okay, so it's quite a huge number. For example, if M equals string 2 and F equals string 1, one generation would need to pass. So the solution would be 1. However, if M equals 2 and F equals 4, it would not be possible. So for example, if you have like, here are the test cases given. If you have 4 and 7, then the output is 4. If you have 2 and 1, the output is 1. So why is it 1? Then we have, so if it is, if there's 1, because if they must be exactly the same. So this is our goal, right? So we have 1. So we have 1 from each initially. So I have not fully grasped the problem yet, but I think we will get there. How can I move this board? No, this is not possible. What? Do color shape text. So, okay. So if you have like M and F is our parameters. Okay, so say M is, what was the example? M is 2 and F is 1. So this is our input to the function. And then we also know that we start with, second, you need to, the replication process can be changed each cycle. Every match bomb retrieves a sync unit from a fecular bomb. For every match bomb, a fecular bomb is created. Every fecular bomb spontaneously creates a match bomb. For example, if you had 3 match bombs and 2 fecular bombs, they could either produce 3 match bombs and 5 fecular bombs, or 5 match bombs. Okay, this I understand. Second, you need to ensure that you have exactly the right number of match and fecular bombs to destroy the lamp jobs. So exactly the right number. So this is what is passed. So our goal is 2 and 1. So now where do we start? Finally, you were only able to smuggle 1 of each type of bomb aboard the ship. So this is our goal, right? Of this function. Where do we start? So we start with 1, 1. So in this tuple representation. So this is the first one being M and the second one being F. So now we can go either in this state, 2, 1, by replicating the match bomb, or we can go in this state, 1, 2, by replicating the fecular bomb, right? So these are our 2 states, and then of course we have follow-up states and so on. But our goal is to find a state where we have this 2-1 state. So we have 2 match bombs and 1 fecular bomb. So 2M and 1F. So we have this state. This is our target state. Okay. So basically, we have this state machine going from one state to the other, and we need to find the final state. And on the way, we need to count the number of steps. So this one is like one operation leads to this. And then if you have another state, say we start with M equals 2 and F equals 4. Why doesn't it work? So say we have a this starting state, this goal state. So this is our goal state, and again we start with 1, 1, Now we can go into this 2-1 state, or we can go into the 1-2 state. And now we want to have 2m and 4f. So if we from this state we can go from this state we can go into 3, 1 and 2, 3, and from this state we can go into 3, 2 or 1, 3. Right, so for every m we can generate an f, for every f we can generate an m. So we can, for these two f's, we can generate two m's and add them to the m's so that we obtain 3, 2, or we can generate from this 1m we can generate 1f so that we enter the state 1, 3. And our goal state is 2, 4. So why can't we reach 2, 4? So now if we again go into this state, so it helps to draw out things to really understand the algorithm. Usually this is very good invested time, so you should do this yourself if you solve some problems. Think about the state, make it crystal clear what you want to accomplish. And so here we can reach the state 4, 1. So you already see it's this tree representation, and of course the tree will explode if we have a lot of so a large inputs, for example, then the tree will explode, so the search space will be really large. Without optimization, I guess it's very hard to solve this problem like in the brute force approach, to simply search the whole tree for the final for the steady state. So we would need some heuristics maybe also. Let's see what we are doing. And so we have again what we can do is 3, 4. And here we have 5, 3 and 2, 5. So now if one number is already larger, we cannot reach it. So this is the state that doesn't lead us anywhere. This state 5, 3 also doesn't lead us anywhere. So here the m is already larger than our target m, which is 2. So this doesn't lead us anywhere. And here we have 4, 1. This also doesn't lead us anywhere because m is already 4. M simply needs to be 2. So here again m is also larger already, so this doesn't lead us anywhere. So the only state that has some potential is this one. So now we can search further. So we have 4, 3 here. Now this state is can already be cancelled out, and here we have 1, 4, and this state still looks okay, but if we now go into the next state, this would be 5 and 4. So this state is done, and the last state is 1, 5, and again this state is already invalid. So we see all of the terminal states are basically invalid, so we cannot find a solution anymore. So therefore this solution is not possible. So there are some impossible solutions, but many solutions are also possible. Okay, so I guess I start to understand the problem slowly. And yeah, so now again let's have a look at the numbers. What can be our input? So write a function solution mf where m and f are the number of match and factor bombs needed. Return the fewest number of generations. So we want to find, like here we have level 1, level 2, level 3. These are our generations. So in each cycle we can generate some. So like these are the levels basically, yeah. So and we want to find the fewest. So the first AND states, because there can be multiple multiple AND or actually success states in different levels. Yeah, after different generations, there may be different ways of reaching to this solution. So we want to find the minimum. So therefore, we have to search the whole tree basically. Yeah, so we cannot afford to simply return the first solution that we find. We need to find the best solution. And so it's an optimization problem. These optimization problems are usually quite hard. Return the fewest number of generations as a string that need to pass before you'll have the exact number of bombs necessary to destroy the lamp job. Or the string impossible if this can't be done. M and F will be string representation of positive integers no larger than 10 to the power of 50. So this is what scares me. 10 to the power of 50. So both M and F can be really large. I mean, they can be quite large. So we will, I mean, 10 to the power of 50. I don't know if Python can handle those large numbers. I mean, 10 to the power of 50. 10 to the power of 50 in bits. So what is this number? 10 to the power of 50. Log 2 to the power log. Maybe then have, maybe we simply, so I don't know, I mean 10 with 50 positions. Say we have 2 to the power of 100. It will not even be, so what, so like 100 bits are not even enough to represent this large number. So we need to have maybe, what if we have 200 bits? Okay, so then we finally reach this number. So we need up to 200 bits to an integer number with 200 bits just to represent a number. So this can be quite large number. But it may be possible by Python to represent these numbers. Okay, so I would say we start with a simple, like the straight and naive approach, and then we can optimize later. This is always a good idea to do this, okay? So let's maybe dive in the code, try the naive approach, and then we move on. Okay, so our start state is 1, 1. So I just represent it as a tuple, right? So why should I so then our input is a string, so therefore we need to first convert it to an integer. So if you have, for example, so I want to have a Python share. So here you see, if you have the, so we can use the integer function. Say we have a very large string like this, then the int function which will convert our string into an integer value. Okay, so this is what we need to do here. So we have a goal state where we simply convert our numbers into integers. Now we have integers in our goal state. Our start state is this one, and now the task is to find the goal state in the fewest number of iterations possible. Okay, and how do we proceed? So one way would be, let's have a drawing board so that we have conceptually. So we have a certain number of states. So this is our initial state, okay? So I call it fringe. And maybe no, let's make it like this. So here we have our fringe. This is our current state, which we have already explored. And now we want to find the next state. So we now we generate our next states, which is like either we have this one as the next state, or this 1, 2, or we have 2, 1 as the next state. So these are all the states that are possible. Let's call it the fringe, yeah, F for F. These are all the neighboring states of states in our core. Let's call this core. And now we can simply move, like we can select one state and move it into our core. So now 1, 2 would be in our core, and we can generate the next states, the neighboring states, right away. So which is like 3 and 2. Now they are in our fringe, 3 and 2. This one is removed from our fringe and moved into the core, and then we also have a state 1, 3. Okay, And this way we always like we need to decide how to select the state from this fringe and move it into the core. And then as soon as we okay, so this is just one algorithm. Of course we can have a I mean a breadth first search. Is it breadth first? Yeah, it's breadth first search. It would be probably the best one, yeah. So sorry, this was just one confusing idea. I'm just thinking aloud. So here, so say we have this one state. I will not just not model the state. And now we have some neighboring states here and here. And again, some neighboring states here and here and here and here. Okay, so we start with this one state, and now we have two neighboring states. So we simply create. So we check, is this our target state? If yes, we are done. We can go. If not, we create. So if not, we create these two states. Okay, so level 2, and then we simply track. Okay, so we have a counter 0 for 0 modifications here or generations. Then we have the counter 1 if we have created one more generation. And we need to create all of those states. And now we check, is our goal solution in our generation. So like this is generation 0, this is generation 1. We simply create the generations here, yeah. And this is gen 2, and yeah, so actually this counter is just represented by this gen number. Okay, so we create the first generation, then we create the second generation, third generation, and so on until we find our goal state. And then of course we have the optimization that if there is a state in our generation that can never lead to our target state, then we will immediately remove this state. Okay, so we will immediately remove invalid states, and as soon as all states are invalid in a generation, we cannot produce any more generation. Okay, so this will be our strategy we use. I think this is a very sensible approach, as a naive approach. Okay, so we have basically we have a set or a list of the current generation. It's initially contains only the start, and then we have a counter. It's initially 0, and now we simply check while our generation still contains some states. So we only need to have check while gen. If gen has at least one state, then this will be true. Otherwise, it will be false, or evaluated to false. So therefore, it will not enter the loop if there's no state left. Okay, and then we have some. So we do some stuff, and if we leave the loop, we return. So if we leave the loop, this means that generation is empty, and we have not. So if we found a solution, then we return the solution here, yeah. But if we didn't find the solution and we have an empty generations, then of course we need to return. What do we have to return? We have to return impossible, the string impossible. Okay, so this is what we want to return. So let's copy the string and we return impossible. I always like the single quote strings. I don't know why. Okay, so we return impossible if we didn't find a solution. If we find a solution here in our generation, then we return the solution, of course. So now we first need to so we need to do two things. We need to generate new states for our next generation, and then we need to check if one of them is goal state, and then actually we have a third objective we want to do, which is remove states that never lead to goal. So there are some states we have seen here. We've seen here that some states, like here, like this 4-1 can never lead to 2-4. So therefore we can remove the state 4-1 from our consideration. Okay, so we generate new states, and to generate new states we actually have to use all the states from the previous generation. So if you go back to the tree, to generate all states from generation 2, we have to go over all states in generation 1 and expand them by one step. So we have to find 2 follow-up states. For each state we have to find 2 follow-up states. So we basically, what we do is for, let's call it, so how are the devices are the match bombs and the fecular bombs. So we have let's call it for M and F for match and fecular bombs in our gen. So now we go over all states from our I think there's a better way of representing it. So we use the pop function for I in range length of generation. We simply pop one element. So now we have one state, one random state from our previous generation, and we use the pop function to remove this state from the old generation. So after this loop is done, basically the generation is empty. So do we have to do this? Maybe not. Maybe we keep it simple, like next gen is initially empty, and then we do it the Pythonic way. For mf in gen, we simply expand mf. Okay, so we basically call next gen extend the current state mf. So we need to basically calculate, so we need to add 2 values to the next generation. The first value being m plus f and f. So it's basically we have to add two tuples here. The first tuple is m plus f and f, and the second being m plus f. Okay, so these are our 2 f plus m. I like it more this way. Okay, so we add 2 states. We use the extend method. Is it extend? No, it's extend. So we use the list extend method, which adds all elements in the iterable given here. And is it the best way to create a list, or maybe not? Maybe we simply do it. Use the append method. Maybe it may be a bit more efficient because we don't have to create a new list. So we call the append method 2 times, next gen append. So this is already, I think, a bit more readable, because now you see, okay, we append 2 elements to the next generation. Okay, so I think we should check first if one of them is the goal state. So we can do this directly here. If m is equal goal 0 and f is equal to goal 1, then we have found the current generation, and this is the generation number is C. So, but I think we have to convert the generation number to a string, and then don't forget to increase the counter in each loop iteration. Okay, go to next generation, we increase the counter, and we set generation, we basically override generation with next gen. Now we could do some memory optimization, we could remove all the previous generation, but I don't think I want to do it yet. Maybe for optimization later we can do it. Because now we will quickly have stale objects in memory. Yeah? So because we will always override the generation variable with the next generation, which is a new list. So the next generation, we just create a new list. We add some states to the new list, and then we set gen to next gen. So the old list where gen variable has pointed to will be loose, will reside anywhere in memory, but it will not be used anymore. So we could remove it immediately using the del keyword, but I don't know, maybe it has no benefit basically. Okay, so what do we want to return? So we return impossible if this can't be done. Return the fewest number of generations as a string that need to pass before you'll have the exact number of bombs necessary. So for example, if you have, if the initial state is already the correct state, like say our goal state is 1 1 and our start state is 1 1, then we will return 0. Yeah, so because gen will be, so we would of course create the next gen variables, then we would go into over all states, which is only one state, 1 1, and then we check m equals goal of 0 and f equals goal of 1. So m is 1 and f is 1. So our start, this is our start state, and the goal would be 1 and 1 as well. So we have m equal, so 1 equals 1 and 1 equals 1. So this is true. And then we would return the string value of our current generation, which is 0. So we don't have to do anything. We simply return 0, which is then our expected result. And then later we will increase our generation. So we will always return the minimum number of generations needed, yeah, through this breadth search. So we only generate a new generation with an additional counter, so with a larger value, with a larger value, if the smaller value doesn't provide a solution. So therefore we are guaranteed to return the minimum number of generations needed. Good. So now this goes forever, yeah. So now this would go forever because it would just generate new generations, new generations, new generations. But now we also need to remove states that can never lead to the goal. So basically, here we want to append these states only if if our number of bombs do not already exceed our goal state. So if at least one number exceeds the goal state, then we can never reach a solution anymore. Okay. So remove states that never lead to the goal. So we simply go over all okay, so if so, I mean, of course, a crude force would be a crude way of doing it would be like this: if m plus f is larger than goal of 0, or m plus f. So basically, as you see here, m plus f. So in both cases, we perform the same calculations, m plus f, m plus f. So one of the bombs will be replaced by m plus f. So if m plus 1 is larger than goal of 0 or goal of 1, and now of course we don't have to calculate this a lot of times. So I have an optimization in a moment. Only then we actually append the states. No, actually not. So sorry. If m plus f is smaller, so if m plus f is smaller than the first goal value for our bomb for our match bomb, then if it is smaller, then we want to append. If it is larger, smaller or equal, then we want to append. If it is larger, then we have already reached a state where that doesn't make any sense to append. And then we also need to do the same for the second goal state, and we append this tuple only if this one is smaller or equal our second goal state for the f bombs. And if this is not the case, then of course there is no need to append it because we have already reached an invalid state. Okay, so let's reformat this a bit, and then we can also immediately see an optimization. So here we calculate m plus f multiple times. This is not needed. So we simply can call it, let's call it n for new. If n, 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 and n. Basically, it may make more sense to call it fm for facular match bombs, or mf basically for match facular bombs. And now we use this variable name. Usually you should not use uppercase letters, but I think in this case we have it's readable because you know that mf is talking about the match in the facular bomb, and yeah, so we can use this. Okay, now we calculate this mf only once. And we can add our comment here. So ignore states that never lead to goal. So these are states that where one of the values, mf, is larger than the goal, the target value. Okay, and then we move to the next generation. So here we generate new states, but we append the states only if they are if they still can lead to the solution. I think there may be an even optimization, but we will look into this later. Okay, so this would be probably a solution. So let's check. Probably there wasn't a mistake anywhere, but we will see it. Print solution. Let's just copy paste this. Copy. So this is one solution we want to check, and then we have another solution. 2, 1, and our target outputs are 4 and 1. Let's write it like this. I will give a bit more space here to the Python code. So okay, so I will just go over the code once more. Okay, so we create the goal state, we convert the string to an integer value, x and y. We have a start state, which is 1, 1 immediately, initially, so we have one m bomb, one f bomb. Then we use our generations list and our counter, and we now first we generate new states, store it in the next gen variable, and then after generating the states we override the current generation gen with the next gen variable, which we have just created, and we increase the state. And how do we generate the new states? So we go over all mf values in our generation, so we iterate over all tuples, and if m is goal and f is goal, then so we can also use tuple comparison, which is probably more effective. So we can do mf equals goal. Yeah, it's more readable, I think. So we go over all tuples mf, and if this tuple is equal to goal, then so if we have found one, then we can return the current generation identifier initially. So if we can do this in the first setting, then it will return 0. If we can return it in the second generation, it will return 1, and so on. So because we have to do like the number of generations we have to create. If it is already, if the first state is already the solution, then we don't have to create any generation. So therefore we will correctly return 0 here. 0 as a string, because we convert it first, and c will be increased, yes, as an integer. Okay, and then we have this optimization. Basically we ignore states only if they can never lead to the goal. So when this is the case, if mf, our sum, is larger than the target value for m or for f. If this is larger than the target value, then we would have this setting here, which we have seen here in this case. So our goal is 2, 4, but here we have already 3, 1. So 2 plus 4 would be, so in this case 3, 1. Basically in this case for 2, 1 we generate the two tuples 3, 1 and 2, 3. But now we check, is 3, which is this m plus f. So we first calculate m plus f, which is 2 plus 1. This is m plus f. So 3 is 3 larger than our first or our second tuple value. In this case, this tuple value cannot be, so this tuple can never be a solution. So we will immediately skip it. So basically here we wouldn't even create this state 3, 1, because here mf is larger than the first tuple value, and we would accept this state because m plus f, which is 3, is not larger than 4. Okay, so we use the goal. We use here our goal, so we check mf is smaller than the goal of 0, and mf is smaller than the goal of 1. Only in this case we append our respective new state. Okay, looks good to me. Let's run this. Okay, well, we need to create a tuple here. Four and 1. So we have the correct solution for those two. Let's see if we have more test cases. So for example, we had this case 2, 4, where it wouldn't be possible. 2 and 4, and here we want to have impossible as a string, and we have impossible as a string. Okay, so this works. the code does what it is supposed to do. So this now it may be an efficiency question whether this is the most efficient way of doing it. Of course, an optimization is to check even more conditions whether we should add a tuple to our next gen variable or not. Because sometimes it may not make sense to add a tuple. Sorry. Okay, so but I think this is at least it's correct. It seems to be efficient to me. We can have more advanced search heuristics. But I don't see why they should be better in the general case. Okay, so let's copy this. So I will use it as a first solution. We may find other solutions later. And now let's verify this. So we use this code to, so let's help. Now we have edit, so we can open a file in the editor. We want to edit solution.py, and now we can copy paste our code here. We don't want to have those examples. Let's save this. Changes are saved. Now we have a solution that at least works, I guess. So let's see the constraints. Maybe we have missed something. Constraints. Okay, your code will be in Java. Your code will run inside a Python sandbox. All tests will be run by calling, it's Python 2.7. All tests will be run by calling the solution function. Standard libraries are supported. Input are not allowed. Your solution must be limited in size, which it is. Okay, so let's check again. README, we have already read the README in detail. So we can submit our solution. Actually, we first check the solution. We run verify solution.py. Now it verifies the solution. It takes a lot of time, so it may be too slow. For large inputs. We should have checked this. Okay, so it failed some tests, probably because it's too slow, right? So what if we have huge inputs here? Like 2. Let's have the maximum input here, 10. So we have string of 10 to the power of 50 and string of 10 to the power of 50. So now we have very large numbers and we want to have the solution. I don't know if the solution is possible or not. Probably not, but so we don't know the solution, but whether it is possible, but we can at least try to run the code and see if it even terminates. Okay, so we close solution, close print. Our solution, no, solution takes 2 arguments. So okay. So now it runs and runs and runs and runs, and probably this is the reason why it fails, yeah? It's just so slow. So our naive approach is too naive, which was what I expected. Because I mean we have 4 days time for this, so probably they want to have a very effective solution. I think we may optimize it with caching later. Because we calculate a lot of redundant solutions. Maybe a set is even better because I think. So let's first skip it. So it runs forever, you have seen, yeah? So maybe even for, let's have a large one. I just want to have one solution for a large input. So let's see if you can calculate 10 to the power of 10. Even here, it seemed to be too slow to solve. So this is an optimization problem. The thing is not to solve the problem. Solving the problem is relatively easy, but solving the problem efficiently, this is a challenge here in this code. So let's have a solution with only 1 million, with numbers 1 million and 1 million. Even here it takes some time, so it takes too long. So what happens if you have, like, say 10,000 and 10,000? Okay, so it's much too slow. It's extremely, it's much too slow. So not even 10,000. Okay, so let's check 100. Okay, 100 is impossible. So let's make it 1000. Maybe you can handle 1000. Yes, you can. Okay, so so if you do some performance optimization, you need to check runtime, whether the runtime really improves. Okay, so our first solution, let's this is our first solution, and it clearly doesn't work. So it works, but it's too slow. So therefore, we need to find a new solution, and we should now basically. So I import time it, which is a nice function to check. But I don't think we can use it here. Okay, so we simply import time. Now we have T1, let's call it T0, which is our start time, time.time. So if you do some performance optimization, you always need to know what is a benchmark, what are you trying to accomplish. So here we have, let's calculate T1 minus T0 milliseconds. I think it's milliseconds have passed. Okay, so we can use the comma separated print. Okay, so here we have, like, I think it's seconds. Seconds have passed. Okay, here 0.473 seconds have passed. Let's make one of the number, let's make it, like, can we have one that is even larger here? I want to find one solution that is doable. Okay, here in 3.7 seconds it calculates this solution. Okay, so now if you improve our solution, then it should still pass those tests here. So we want to have 4.1 impossible. And impossible seems to be the correct answer for our last test. So here we want to have impossible as well as output. So our output should be 4.1 impossible impossible. And then we want to have here this, so initially I just copy paste this output, so we want to beat our 3.76. So this is now our benchmark. So we want to beat 3.76 seconds. And can get rid of this white space. Okay, so one optimization I found is, I think this is a huge optimization. So here we use, as next gen, we use a list. The problem is that by using a list is not duplicate free. So we will have a lot of duplicated states here. So why is this the case? Because if you look again into our tree, so we start with 1, 1, then we have 2, 1 here, and we have 1, 2 here. And now if we add those together, we have 3, 2 as a state here, and 1, 3 as a state here. And here we have 3, 1 and 2, 3. Okay, and now these states, they may overlap. There may be duplicates, yeah, because we can have the same states from different branches. And in this case, we don't want to add all these duplicates, because the duplicates doesn't really give us any additional information, right? So here, for example, so let's generate a few more to see whether we really have some duplicates, but I'm pretty sure there are duplicates. So here we have 4, 1, here we have 3, 4, then we have 5, 3, we have 2, 5, we have 5, 2, and 3, 5, we have 4, 3, and we have 1, 4. Okay, still no duplicates. But now if we calculate here these ones, we may find, we may see some duplicates soon. 7, 4. So because there are only so many integers, so they won't be, there will be duplicates, I'm pretty sure. 8. So, but yeah, so even if you, so actually 5, 4. And do we already have duplicates? So there we may even have duplicates. So the problem is we may even have a state here that we also explore later in a level, in a later level, right? So we also, so if we have two states, for example here, this is a second optimization. If you have two states here, then we don't need to expand this state as well, because we have already expanded this state. Okay, so therefore we also need to have a cache later. Okay, so one optimization is we use sets. Why sets? Because sets are duplicate free, so we don't want to have duplicates in our generation. A second optimization is to have a cache. In the cache we store all tuples already explored. And the tuple already explored, we don't want to explore again, yeah, because it's just redundant. If we have explored a tuple and we explore a tuple again, then this will generate infinite number of states that are actually unnecessary. Because then this tuple, when expanding this tuple, it will generate exactly the same. It will generate itself again and again. So it will really, I mean, because say we have like one state here that further down the line generates another state. So say we have, no, okay, this is not an issue, but still, I mean, still we have, we may have in different branches, like here we have 2, 1, and we may have 2, 1 later, in a later state, somewhere down the line. So we want to have a cache. And the cache, we want to ignore states we have already seen. So ignore states seen. because it just doesn't give us anything. So if you have, say we have explored 2, 1 already, or in more general, so if you have a value n and value m, and we have already explored those, and then later in a different branch we also explore, we have later also nm, then exploring this state doesn't make any sense because we are already in the process of exploring this branch. So even if he finds even if there would be a solution, this solution would be worse. So even if like down the stream, so somewhere here, after say x steps we find a solution, then we would also find after x steps we would find a solution here in this branch. So therefore this branch, as it was explored earlier, will generate a smaller number c, which is our generation state. So therefore we will, so if this is c and this is c tick, then c will be smaller than c tick. So therefore c is the correct solution, and we can simply get rid of this one. So therefore we want to have a cache of scene states. Of course, maintaining the cache is also some overhead, so we have to see whether this really helps. But first of all, I mean, the easy optimization is to use a set here. So with the set, we have duplicate freeness. Next gen, this one is also a set. And I think the set operation is add. Okay, the set operation also is an iterator. The set is an iterator, so it allows us to iterate over all states in the set. So this is possible. And then next gen is a set, so we simply add those. And we go to the next generation here. Okay, so this should also now return the same one and produces better. Oh, it's a dictionary, so it assumes it's a dictionary. So let's just make it like this, initialize it like this. And here we also have an empty set. Okay, so this is actually, it produces the same output, but it's slower. I didn't expect this to be slower. But the thing is, it may be faster for larger inputs. So let's maybe do the following. We copy paste this solution. And now we roll back. So, and we call this the old solution. And we call this solution. Okay, so then we have now we first evaluate the old solution. So we have old. So I will just make it a bit more concise. And then we also have a new. And here instead of solution, we use the function old solution. So now we directly compare both outputs and both runtimes. Okay, here we have old, it's 3.7 seconds have passed, and new, it takes longer, 7.6 seconds. So this is this may be the case for so, but what happens if we make it run even longer? So probably this will take a lot of time. But it may terminate. I just want to check. Okay, otherwise if this doesn't work. Okay, let's keep it like this and simply double. Okay, now it actually terminates. So this one needs 37.9 seconds. I just want to observe the memory and process overhead on my computer. Okay, you see CPU is 65% loaded, and also my memory is quite full. Memory is full with stuff. It's full with this old lists and sets, basically sets in our case, in the current case. So it, like you see this zigzag behavior because it is always filling up the memory, and then the garbage collector in Python removes stuff from memory and so on. So it needs a lot of time. So let's see. I mean, this one took 37 seconds, so less than a minute. So I think we may be already slower than the previous solution. So I still think using sets is the way to go, maybe, but maybe this, because sets have a better runtime complexity, but the constant overhead of sets is larger. Okay, so therefore for smaller inputs, I guess for larger inputs it would still be more efficient, but I mean we cannot observe it here. So let's again make this 10 to the power of 3 and 10 to the power of 3, so that we have some comparison that doesn't take too long. And then let's keep working on our solution, right? So we have sets. So here we can quickly check. We can tie this. So as a first thing, we can check if we have already terminated. Yeah, so we simply check if mf in our set, in our gen set, then we directly return without even iterating over this whole thing. And this membership operation, the in operation for sets, is constant runtime. So therefore, it's very efficient. It's much more efficient than lists. If you want to check membership in lists, it has linear runtime. So you need to check the worst case for all elements in a list. If the list has 1 million elements, and it will have 1 million elements, then membership just kills you. But membership for sets is pretty fast. So it just checks, okay, the in operation here, in generation, is constant runtime. So even if it has 1 billion elements, it will just take like a split second to check if this tuple is in the set. And the tuple is a mutable data type, so therefore it's hashable, so you can place it in a set. It's not as an immutable data type, it's hashable, so you can place it to a set. Okay, so now in this, before we do anything in a generation, before we do some random work here, iterating over the tuples, we simply check if our goal tuple if our goal tuple, so we need to basically check if goal in gen, not mf. So if our goal tuple is in our current generation, then we return the current generation number. So here we checked whether for each tuple whether it is equal to the goal. So this is a lot of overhead. It's very inefficient because now we need, for each generation we need to check. So if you have a million, okay, so this is very inefficient. If you have a million elements in our set, then, or in our list, then we have to do 1 million checks whether this element is in the goal. So this is what we are doing here in this example. So we do the million checks, which is very inefficient. If we do this one here, we do the check not within the for loop, so we don't have a million checks. We have only a single call of the function goal in generation. Single call instead of a million. So now we have like a million times improvement, or billion times if you have billion tuples in our generation. So therefore this is much faster. This is much more efficient now. So only this should already improve runtime, but let's check if I'm correct this time. So the old one takes 3.9 seconds. Okay, and the new one is still slower, 6.6, but at least we are faster than the previous one. Yeah, so we have and of course this optimization will be really efficient towards the later if you have more elements. So now these are relatively small inputs here, yeah, so with 10,000 and 1,000, but we will have inputs of 10 to the power of 50, so we will have really big inputs here, and therefore towards the end this optimization will really count. It will really matter. So therefore we will keep this optimization in. And we will keep using sets instead of lists, because for lists it is just inefficient. It may be more efficient for the small inputs, but for large inputs it will be more efficient for using sets for sure. Yeah, just because checking membership for sets is constant runtime complexity versus linear runtime complexity for lists. So now we again iterate here overall. Yeah, probably like dynamic programming, a whole different algorithm would be needed here. We'll think about this for a moment, but let's check if our larger one, if our new solution can handle larger inputs. So let's check 10 to the power of 4, both of them. Now, of course, we cannot compare the old with the new solution, but I just want to check if the new solution is now at least able to calculate for 10,000 elements. But I think I may have to change the whole approach to be even able to calculate this. So previously it took us 95 seconds for the larger one. My prediction is that we are now faster, but as it calculates, I will start thinking about a new solution. Okay, so we have we have F and we have M. So we start with 1, 1. Okay, let's maybe again go back. So we start with 1 1. Now we have 2 1 and 1 2. Now we have 3 1 and so I think there may be something with dynamic programming. It's a good algorithm. There's a good book. Let's see if I have it here. It's called Introduction to Algorithms. This book from it's not one of my books, from Thomas Corman and Rivest and Stein. So it's a really popular book. It's very thick book, and this book contains a lot of good algorithms. So if you need to improve your algorithmic understanding, then check out this book. It's really a nice book. Okay, dynamic programming is here. We have something like this. We have a start state, we have follow up states, and we have a goal state. I want to have a visualization of this. So here we have plus 2. 2 is our MF. So we have our plus 2 here. Here we have plus 3. Here we have our plus. Actually, no, it's not like this. So are we already terminated? Okay, 98 seconds. So the optimization kind of helped, but it's still a long shot. So if we are using caching, so I will just try to use caching one more time. Say we have a cache. Initially it's an empty dictionary. And ignore states that never lead to goal. Okay, let's use this variable here, mf. And so these are our states, and then we add the state to it. Now we can check for each state that we have explored. I wonder, I mean, this cache can also grow quite rapidly. Because we will have a lot of states in the cache. So we need to have a cache dropping mechanism. I don't know if this lazy approach helps us a lot here. So at least we will get rid of all redundancy, right? And so here we check if state in cache, if state not in cache, only then we will add it. Okay, so we add another layer of protection, so to say. So we check if the state is not in the cache, we add this new generation, and then what we also do is cache. We set cache of state. And we don't even need a cache. We just need to have a set, basically. Yeah. So we call it just a scene set of all scene values, and if our state is not in scene, we will basically and now you can already see that now we keep track of all the states we have ever seen. But this may not be a problem because here we have a binary tree, and a binary tree doubles in value, so it doubles the number of leaves in each layer, basically. Yeah, so we double the number of leaves in each layer. So therefore, so the sum of all values in the whole tree is more or less the same than the number of elements in the current layer, so in the next layer. So basically this layer has approximately as many elements as this layer. So what we do, if we keep track of the scene state, we only double our memory usage. That's it. We don't do more. So we double our memory usage, but what we gain is that we don't do some computations. So we use more memory, but we skip a lot of computations. But we use only a constant number of times. So like basically we only double the memory usage, but we like exponentially improve our probably exponentially improve the number of states we visit. So this may be an efficient optimization. Okay, so we check again. So let's go over the code. So we have a variable scene, which is initially an empty set, and then we check for each state. So here we calculate MF. Then we check if MF is smaller than our first goal value. So in this case, we create a new state MFF, and we add the state to our next generation. But only if the state is not already seen. If we have already seen it, we don't add it to the next generations because we have already added it to the next generation. So therefore, and then we keep track of all the scene states which we have added. Okay, so there's some redundancy here. The code can be improved, but I would just try it out now. So now we still have we have used cache, not in scene here. So this is a problem if you have redundant code. If you change it at one position, then you also need to change it at another position. Okay, so now we still have 10 to the power of 4 elements. Whoa, and now it's much faster. Whoa, okay, so it really has improved the output. You can see now we have even, so our second approach has now 10,000 elements in both. So we have 10 to the power of 4, so we have 10,000 as input values for M and F. And here, so we have a higher input here, by an order of magnitude higher input here, but we have still a faster solution than our previous old solution. So therefore, I think we can safely now get rid of the old solution, basically, yeah. And so I think this is a good approach that is much faster. So I will keep track of this. As a second solution, I was right that the first solution is not sufficient. The trivial approach kind of is not the way to go. It's too inefficient. Okay. So let's try, shall we try even, so I will now remove the old solution completely because it just doesn't make sense to even keep it. Now we also remove this old thing. You can remove this one. Okay, and our new solution, so we can also remove this one. So we have our outputs. Our goal outputs is our new solution produces an error. Okay, so there's an error. So because here we have 4 and 1, and here we returned 4 and impossible. So why is that? Okay, so why doesn't it work for the second output for our solution 2, 1? So we have 2, 1. So our goal state is 2, 1 here. So let's try this out with this algorithm. Why doesn't it work for 2, 1? Now we set start to 1, 1. We initialize the gen. We enter this one. If goal in gen, which is not the case, then we generate the new states. For mf in gen, so this will be like we will only enter it once. So we have 1, 1, 1, 1 in gen. So now we calculate this as 2, mf is 2. So now we check if 2 is smaller than goal, the first value of goal. Is smaller or equal first value of goal. This is 2. So it is smaller or equal because 2, mf is 2, so 2 is smaller or equal goal 0, which is 2. So this is true. So our new state is 2, 1. to 1, and if state not in scene, we add to the next generation. And we also add it to the state. So we add the state to 1 to the next generation, and now we check if 2 is smaller or equal than 1, which is not the case. Then the goal 1, which is not the case because this one is 1 here. So and MF is 2. So we have 2 smaller equal 1, which is false. So we don't enter this branch. Then we go to the next generation. Gen is next gen. Here we have added one state, the state to 1. Now we should check if goal to 1 in gen. So let's maybe print the generation each time we enter it here. Print the generation. Okay, so here this second time we only have 1 1 in the generation. So this is our starting point, and here it generates impossible. So we don't even add the state. If MF, so let's comment this out. For the first one it works, yeah. Ah, okay. Okay. Yeah, the problem is that we didn't refresh the scene variable. Okay, so we have basically, we shouldn't initialize the scene variable here, we should initialize it here. Otherwise it will use the variable scene from the previous execution, which is of course not what we want. Okay, so now we don't need to print everything. Let's skip computation here. Now my computer is clearly not capable of handling the load. Now I hope that I still have the old solution, code.py. Okay, now we set scene, we initialize scene within the solution. Okay, let's run this. For 1 impossible. Okay, that's why it was so efficient. So we still have do not have a very good solution, unfortunately. So I was too optimistic. It's still slow, still takes time to run. Okay, so we need to have a different approach. I don't see how this can ever turn out to be efficient enough to handle this huge number of 10 to the power of 50. Okay, so again, so we have a state. So we have a state xy, and to go in the next state, our next state is either 2x plus y and y, or x and 2y plus x. So I just play around with some mathematical stuff now. Okay, so we have this, in the general cases we have state xy, and now the follow-up state is either 2x plus y and y, because y is unchanged. Ah, no, sorry, sorry, forget about what I just said. So the follow-up state is either this one, x plus y and y, or it is this one, x and x plus y. For any given state, this is the follow-up state. Is there a closed formula or anything that I don't see? Okay, so what if we have... I just try different ideas now. So what if this one, what if it is a two-dimensional space? So one dimension is our M, and the second dimension is our F. And now this is our starting point, right? At 1, 1. So this, like, here we have value 1, here we have value 1. This is our starting point. And now somewhere in this space we have our solution. Like, say our solution is, this is star here, yeah? So we have, this is our goal state which we want to reach. Say it is x and y. Yeah, it should be the other way around, because I mean the first one would, so let's make it really visually correct. So we have M here and F here, right? Because our M, yeah, so M equals 2 and F equals 1, for example. Okay, so now we have two-dimensional points. And now, I mean, those are, so basically all the points in the space are possible points. It can be visited. Actually not, we cannot visit all points. And now in each step we go either up or we go to the right. M plus F. Okay, and here f is equal 1. So we have already seen like this in combination with the previous example here. Can I just cut everything and move it? No. Okay. So again, in state MF. So say we are in state MF. Now we can go either. So now we have two ways. We can either go up or we can go right. How many steps can we go to the right? So we can keep M as it is. In this case, we would go up. Or how many steps would we go up? We would go up plus F steps. No, plus M steps. We would go up plus M steps. Or we would go right plus F steps. So I think I'm onto something, maybe. Okay, so this is our current state, MF. It's a two-dimensional point in the space, yeah. So we have the value for dimension M and the value for dimension F. And now we can go. These are the two options we have. So we can either go to the right or we can go up. If we go to the right, then we basically add something to our first dimension. And what do we add? We add F to our first dimension. So we used F to replicate. We replicate F and add the result to the variable M. So therefore we go F steps into this direction. Or we go M steps up. And then here we reach the point M is the same. So now we have M and M plus F. And here we have M plus F again, and F stays the same. Okay, isn't it like so? Again, if we are in our two-dimensional space, here we are in a new state. So let's examine this new state. Again, we can keep the first tuple value, M plus F. We keep it. No, basically we keep the second tuple value F, so we keep the Y value in our space. So now it's a bit confusing, yeah, but we have these two axes, so we keep the second axis. So each time we go to the right, we just go to the right. So therefore the second tuple value will not change, right? So therefore in the next example we will also go plus F. And in the next one we will also go plus F. So therefore in our space we have, so basically for a point here, for any point, we only have to look at the multiples of F. So we can have plus f plus f and so on until, say, we reach this point. So we can basically check whether y is a multiple. This is an interesting approach. We can check if y, our target value, no, actually it must be, so y stays the same, right? No, can you do this? So because now if we land here somewhere, then we don't have to so from here we can never go up. So therefore if we fall out of this range, we can simply discard this point. So just going to the right will not help us. Okay, so we can, so actually in one row we have this constant difference between, so these are all the states we can visit in this whole line basically, yeah. So now we can either in each step we can add basically the this first dimension value. So if we can go to the right or we can go to the up. So if we want to go up, what can we do? So we can either add, so here in this case, if you want to go up, then we need to add something to the second tuple value, which is this f value. And what can we add? We can add the first tuple value, which is this m. So we can either go a small step up. Here we can go 2 steps up. Here we can go, say, 1 plus f steps. And here we can go up like this. So it's like this, right? So it will only increase the number of, so the more we are, so now we have this traversal kind of, yeah. So we can basically, if you draw it like this, then it's restricts our possible solution, doesn't it? So it's the same here. We always have, so we have a constant. So say we are at this point here. Now we want to go up plus m. So if you want to go up plus m, then if you want to go up, then we always go up plus m. And as m stays constant, we again go up plus m. So here at this, so basically we have a grid of possible values. We could theoretically outline this grid very rapidly. I mean, we could generate the grid very quickly. It would be very simple to generate this grid. And now the only question is to, yeah, I mean, we can generate this row very quickly. Boom, 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 boom. Have generated all values in this for this value. Then we go one step up, or m up, boom, we go this whole thing quickly. So we can go row after row, we can generate row after row and column after column. So say we start with the first row, then we generate the second row, then we generate the third row, and so on. So this can be done quickly. For each point we can generate all the points. So let's again, so we have our two-dimensional space, we have our target, and now we start here at this point, and now we can generate all points, boom, 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 very quickly, iteratively, until we reach this boundary. Okay, and then we simply take one of those points, say this one, and we generate boom, 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 all of those. And then we take one, say this one, and we generate all those points, boom, 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 boom. It will be fewer points now. Why will it be fewer points? Because we add to the, so let's call this the x dimension, that is the y dimension. So because we always calculate plus y here, yeah? So we add y to the x value, boom, 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 and y is now larger, so therefore we will have fewer points here. And then again here we will have fewer points like this, and we will have fewer points like this, and fewer points and fewer points, and boom, we generate all of those points. So for each point we have generated, we can of course generate new points. I mean, for this point we don't need to generate the points here in upward direction because we already have, yeah, previously. And we don't have to generate the the points that follow here into this direction. Okay, man, I see it. So here in this direction we have already generated when coming from the bottom. Okay, so when we visited this point, we generated all points to the top on this row. So these are all the points that are possible for this x value. So therefore, if we later visit this point again, so we later don't have to visit this point again because we have already generated all the points to so all upward points here. And also in this direction, I mean, if you have already generated a point here, then we will not visit this point again, because we have already generated all points on this y line, straight line. So we have like this straight line grid, right? It's a grid somehow, and we start here, we generate all the points to the top. So what we previously did, we had this fringe, we calculated the follow-up point, so we calculated this point and this point by summing this up. So basically, then we generated this follow-up point and this follow-up point based on some calculation. We put everything into the fringe, but we would have, probably we had a lot of redundancies, right? So, but now we don't have any redundancy. It's just an iterative approach. So now we don't have to introduce a cache or anything. So it's just an approach without redundancy. Let me quickly think about this for a moment. Okay, so we can quickly check for one. So say we have created, so for one y value, say this is y equals 1 initially. Now boom, 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 we create this whole, all these points by adding just x, by adding y to the x value. So we have +1, +1, and so on. Boom, 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 boom. We create all points. And now, so from each of those points, we can go up, up, up. So we can quickly basically check. No, can. It may not be so easy. So let's have an example. Maybe an example will help. So I will quickly maybe use approach. I'm quickly calculating something on a piece of paper. So if you want, you can also think about the problem. I think it's good to follow along. So think about this grid idea. How can we quickly generate all points and check for each point to go to this target? Okay, I think I may have found a solution, so or a good representation of the data structure we will use. Okay, so again we have our two-dimensional space. This is our y-axis, and this is our x-axis. We start with this point. We want to go to our target point here. So like this is our boundary. Now we can, so this one is a 0 because it means in 0 steps we can reach this point. Now we can in 1 step reach this point. 2, 3, 4, so we can go to the right. So we can directly generate all these points, 5, 6. Okay, and now we do the same on the y-axis. We have 1, 2, 3, 4, 5. Now these are all our generated points. And now what we are doing next is to choose the points with the smallest number. Yeah, so we choose, so one of those 2 points. So we have 2 points with the from this generation 1. So basically here we create points in different generations. Yeah, so we create points up to 5 generations here. So this is different to what we did previously, because previously we created all points with generation 1, then all points with generation 2, then all points with generation 3. And this is kind of expensive to do this. But here it's very cheap to calculate these points of those generations. But of course these are not all points of generation 4 we have generated. We have just created 1 point of generation 4. But now we take all points in generation 1 and generate for each of them, we generate all points in higher generations. Okay, so we take this point 1, and now we create all points in higher generations. So now we create point generation 2, because in 1 step we can go here. But now as y is, so the y value is 2, so now we have y equals 1, y equals 2, y equals 3, y equals 4, 5, and 6. And we have x equals 1, 2, 3, 4, 5, 6, 7. Okay, so this is our number in the two-dimensional space. This number here means just a generation. So it's just our generation identifier. So now we can go in 1 step, we can go from this point to this point. And then in 1 further step, we can hop 2. So because I mean each point x, y, so if y stays the same, then we add y to the value of x. So y is 2, so therefore we add y to the value of x, which is 1. So we have 1 plus 2 is 3. So therefore we have this point. And then we simply add y again to this point, which is 4. So we go to 5, because 3 plus 2 is 5. So therefore this one would be 3, and this one would be 4. Okay, so now with this point we are done. With this one we are now also done. For this we have generated all follow-up points. Now let's generate all points for this one. For this one we can go 2 up. This would be generation 2. Then we go 2 up, it's generation 3. And then we cannot go up because this would exceed our target generation. Our target is 7, 6. Okay, so now we have also generated all for all points in generation 1. Now we do the same for all points in generation 2. For this we can quickly, so here we have the x value of 1. So now we keep the y value in, so now we go right, then we go up. So let's first go right. So here we have y value of 3, so therefore we move by steps of 3. So therefore we can go like 1, 2, 3, we go here, and this one is generation 3 now. And then again we go here generation 4. So so now we have created the horizontal points, but now we go up again. So because we still have to create for this point, we can go in one step, we can go to this point. Yeah, so we can like hop in one, because the y value is, oh no, the x value. So if we go up, we have to take, no. If we go up, we have already calculated what we can do. If we go up, we have already calculated it in the first approach. So therefore we don't have to even check, because there's already a, yeah, we don't have to check. So if we have a conflict, so because here if we try to go up and we boom go up and we have a conflict, then we don't have to basically check this tuple again. This is similar as the approach we already had in our previous solutions. So we don't check tuples that we have already checked, right? So because now here from this point which we are currently examining, we could go in one step, we could go here, but we have already done this basically. So therefore we don't even consider it further. So basically later what we are doing is to store for each generation, we have a list or a set of all values that we, of all points in the space. So let's do it like this. So I was just thinking, what data structure are we using? So now we have the data structure generation. It's like a, can be dictionary, for example. And here for generation, we have generation 0, we have generation 1, 2, 3, 4, and so on. And for each one, we store probably a set of all tuples that we have already produced, that we have generated, yeah, in this space. So now, for example, yeah, so we have, like, for example, currently we are looking at generation 2, and for generation 2, so in generation 1 we have the tuple 1, 1. And in generation 1 we had tuple 2, 1 and 1, 2. So we have 2, 1. Now what is this? And 1, 2. Okay, this is a 2 and this is a 1, and 1, 2. And then for the second, for this second generation, now we have to look at all the 2's here. So like this would be one tuple value we store, this would be one tuple value, this one would be one tuple value, and this one. And then what we are doing is simply, for each one we have a routine. So for each one we check, boom, 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 go up, go right, add all the tuples that are generated to the respective generations. So if we like boom, 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 or add all of them to the generations where they need to be fit, and boom, 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 we generate all of them, and then we get rid of this point. So we don't consider it anymore. So we move to the next point in 2. So now we do the same for here, boom, 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 and we do the same for here, boom, 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 and the same for here, boom, 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 and boom, boom, boom. So we generate for each of the generation 2, we generate all the points in the upper levels, and then we move to generation 3, to the next generation. And now we do the same for all of those in generation 3, boom, boom, and boom, boom, boom. Okay, like this. And then we move to generation 4 and so on. And then as soon as we find a solution, bam, we return ready. Okay, so how do we do it? How do we implement this? Again, we use this data structure here of, we have the generation, we have a dictionary. This is a dictionary of sets. Dictionary of sets. So then we initialize it with this. We go over all tuples in the set, and then for each tuple we call this expand function. And what the expand function does, it fills a dictionary, so it calculates here. So 1 1 would be, so we go all the way up, so it would be 2 1, 3 1, 4 1, 5 1, 6 1, 7 1, 8 1, 9 1, and we go all the way right, and we go all the way up. So up would be so 1 1, then 1 2, 1 3, 1 4, 1 5, 1 6, and all of those are added to the next generation. No, actually, yeah. So we have 1 1 to the generation 1, 1 2 to the generation 1. Then, of course, I mean we have to do the respective. We have to sort it into the correct bucket of the generation. And so if we need one operation to go to this tuple, then we need to increase the generation by 1. If we need 2, then by 2, and so on. So then this kind of this generator function, it would be then a function that takes a tuple, it fills, it updates the generations, all the generations up and all right, maintains this data structure, and then we move on to the next one. But it's really fast. I mean, it's really fast to generate these points. It's fast to access a generation list in the dictionary and a generation set and update a tuple. It's fast to iterate over all tuples. So all operations are basically pretty fast. So I guess this solution should be very efficient. Let's see. Okay, so I will call this old solution. And I will create my new solution, XY. So, is there still something running? No. Ah. Okay, so it is still computing from the previous. Therefore, my computer is really loaded. Now let's see if the load goes down. Okay, now it seems to be released. Okay, let's open the Python shell again. Okay, so we have solution old. And now we have a solution new. It's still kind of slow, my computer. Firefox is now taking everything. So let's get rid of what we don't need. Don't need this. Okay, so our new solution. So the idea is we have this gens, it's a dictionary. So now we fill the dictionary. So the first generation is filled with a set. And what is in the set? We have the tuple 1, 1 in the set. And now, of course, we need to also know this goal state. And okay, so this is our initialization. So we have started with this first tuple in the first generation. And now we have a loop. So for now I will just keep it as while true loop, so a loop that runs forever. So our we start with generation counter 0, and now we will have we will basically check for the whole. So we have for all tuples in our generations of C. So we do something for all tuples in generation C. So we let's call it M and F, this tuple directly. So this is my tuple MF in the current generation, which we are in. So we basically now we generate follow states, and then we have generated all following states and added them to our gens dictionary. Then of course we check it's like it's generate and integrate follow states, and so I need to quickly pause the video. coming back. Good, so I'm back, and I have actually thought a bit about the problem, and I realized something. So if you again we have our space, yeah? So I think this was a good idea to start with the space. And now this is our start point, okay? So our start point is like 0, 0, for example, yeah? Or start 1, 1. And then we also have our, so this is the x-axis and the y-axis, and we also have our goal point. And our goal point is, for example, it may be, I don't know, say it's 5, 2. And so it doesn't really make sense, so maybe it should be maybe a bit more. So let's have another endpoint. Say this is something realistic. Here we have maybe 10, and here we have 7. So 10 on the x-axis and 7 here. So now what we tried is to come up from this, to start with this starting point, and then go to the stop, to the end point, to our goal point. But actually this may be far more difficult, because there are so many options to do this, than to just look at the numbers. So because you know, if we have, what we already discussed previously, where was it? So our formula, this is our formula. So to go from this point to that point, we calculate, we use the original m and calculate m plus f. Okay, so therefore now the y point is larger, and this gives us some information about reverse engineering. Okay, so here in this setting here, in this case, our y point is larger. In this setting, our x point is larger. So therefore, so you know, so one point out of both points will always be the larger one. Why? Because one point is m plus f, so it's the sum of both, while the other one is one single point. So therefore one point will be larger, and we know that here, if for example if this y point here is larger, then this means that we have just added something to the y point, so therefore we need to subtract it again. Okay, so for example in our case here, so in the perfect solution to reach this goal point, we could, so it's the only option is that we have reached this point by subtracting 7, by adding 7 to the x value. Okay, so because there are, I mean, this is the only, how can I describe it? So if you have x equals, so I will just give you both points. So we have this point, it's 3 and 7. No, actually it must be like 7 and 3. So maybe let's erase this. So okay, now I think I know how to explain this. Okay, so here we have x is the same here. X is still 10. Only y is smaller. Okay, so y is, say y is, what can y be? So it's actually not possible. It's not possible to find a way. So if the x value is larger, this means that we have just added something to the x value. Otherwise it wouldn't be larger. I mean, if we had it, so for example, if we didn't have, so if the larger value remained unchanged, then this means that we have, so what value can we put in now here in order to make this consistent, in order to add those two, the sum of both, to the y value and reach this point? It's impossible. I mean, you cannot. So for example, if you put in 2 here, then the next, so then going upward, x remains the same. This means that we have to add 12, the sum of both points, to the y value, and this would make the y value larger. Okay, this is understandable. So because say the y value was, say the larger point remained, so say we remained unchanged, the larger tuple element remained unchanged. This means that in the previous step, the sum of the larger element, which was unchanged, plus the other one would have to be added to the y value, which would mathematically make the y value larger. So it's like it's you can prove that the only way of getting there is actually to calculate the larger minus the smaller value. Okay, so in this case, we calculate 10 minus 7 is 3, and 7 remained unchanged. The smaller remains unchanged. Okay, so this means that we are now at this point 3, 7. Okay, and in this was the last step we did to reach this point. So we kind of reverse engineer the solution. Okay, now we have 3, 7. And now again the same argumentation applies. So if 7 is the larger value, this means that we just added the sum of both to the y value to obtain the larger value. So therefore we need to calculate 7 minus 3 is 4. So and 3, the smaller one, remains unchanged. So we have, like, the next value will be, so 3, the x value is unchanged, the y value changes, it's smaller minus the larger. Because now if you add them together, 7, no, it's not 7 minus, yeah, okay, now, because now if you add 4 plus 3 and you replace it with the y value, then you would obtain this point. Okay, you could not have come from the left here, because it's just not possible to add the smaller x value then in this case to the y value and obtain the because here, yeah, as I already described, so you can only you always have to, like, the algorithm is to take the larger one, subtract the smaller one, and then you reach the previous point. You kind of reverse engineer this. And now again we take the larger one, subtract the smaller one, and then we reach the next point. So we have 3 and 1. We reach this point, and now the x value is the larger one. So we calculate x minus this one is 2. So we have 2, 1 as next point, and then we calculate 2 minus 1 is 1, and we reach this point. Okay, so this is the only path that can lead, like, in minimum steps to this final result. Okay, so I think this is a very elegant solution to just reverse engineer, so both options basically. Yeah, so you can mathematically prove it's so say you have maybe we are doing it, maybe it's helpful to do this, I don't know. So say you have, like, x and x plus y. So in this case you have added y to this element. Okay, so the previous point was xy, this one, right? And now this one is larger, so this is the only way of reaching this point. So one of them is larger, and the larger one is, the larger value can be so, like, by definition of the problem, we have, so one element will be x, the other one will be x plus y from the previous definition of x and y. So this is how we construct a solution based on two values. We do either this or we do that, x plus y and y. Okay, so in this case x, y, so say we are in this case, we either go into this direction or we go into this direction. So we either add y to x or we add x to y. And if you are in this scenario, then we know, because one of them is larger, so always one will be larger. And if this new value for y, let's call it y tick, if this is larger, this means that this has just been changed. So we need to, in order to come back to the original value, we need to calculate minus x. So we take this value, we calculate minus x, and then we get to this point. This is the only solution that leads us back. This is the only solution, this can be the only source, because always the larger value will be the one where we just have added the smaller value. Okay, so this is just this algorithm which we use. Okay, now we have here the larger value. This means that just we add the smaller value to this larger value, the other value that remained unchanged to the larger value. So we can simply calculate larger value minus smaller value to reach this solution. Okay, so one algorithm is to do exactly this one, yeah, to just start from this point and then move, go backwards, sozusagen, go backward and reverse engineer the solution. There's only one problem. Let's have an extreme scenario again. There's one problem if you have this scenario where, so here's our starting point and here's our goal point, and this one is our y value of 1. Say this is now 50, yeah, kind of, let's make it 10 to the power of 50. So this is a huge point here. It can be 10 to the power of 50. This means that now, so the x value is 10 to the power of 50, the y value is 1. So therefore, we need to calculate minus 1, 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 because always this one will be larger. Okay, so we calculate minus 1 a lot of time until we finally reach this this value. Okay, so in this case, we will have how many subtractions? We will have 10 to the power of 50 subtractions. Which is such a huge value, it's probably very inefficient to do. So therefore, the more general approach is to calculate modulo. So we calculate, in this case we can calculate, so if x is, say we have xy, now we take the maximum of the one, so this one is, so if it is much larger, then we want to do this in one step. We want to reach this point in one step. And we do this by calculating, so x modulo y. And x is a larger value. And now, so we divide basically. So this one gives us the remainder. So basically, how many times we hop here with a larger value. So if the value x is larger, so so say we have like this, so x is larger and we subtract y, we subtract y, we subtract y, and so on. We subtract y a lot of time. How often do we have to subtract it until we reach the point where the other one is larger? So we basically have 50, 10 to the power of 50 divided by 1. So many times we have to calculate minus 1. And then we need to check what is the remainder. So basically we perform integer division and then we have a remainder, right? So we calculate x divided by, so this is integer division y. It gives us a value. So say it is 10, for example. So basically, let's maybe have another example that is with real numbers that we can use. So here we have say we have 10, and here we have 1. Okay. And now we need to do like this is one operation to reach 9, 8, 7, 6, 5, 4, 3, 2, 1. So we have 1, 2, 3, 4, 5. So now this is 9, 8, 7, 6, 5, 4, 3, 2, 1. This is the point we want to reach. So how many operations we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 subtractions. Okay, so we calculate 10. So how often so like x is 10 and y is 1. How often fits y into 10? So it fits 10 times into 10. So but we want to calculate basically how can we efficiently represent this? So in another case, say we are at this point, at 10 and this one maybe 2, for example. 2 and 10. So we have this point 10, 2. Now we would have to calculate 8, 2, 6, 2, 4, 2, 2, 2. Now it's done, okay? So 2, 2, and down, and now we calculate like we take any what happens if it is the same. So 2, 2 it cannot happen because one always has to be larger than the other one. So if they are the same, then we can never reach it basically. Okay, so we take the larger one, and now I want to have 1, 2, 3, 4. I want to have 4 as a result. So this one should result in 4. And I want to have the point 2, 2. So I take the difference of both, 10 minus 2, and divide it by 4. No, sorry, it's not true. So I take the difference of both. This is kind of the this is what I need to fill by subtracting the smaller number. So I divide this by the smaller number. Okay, so in this case this would be 8 divided by 2 is 4. So I get 4 subtractions, 4 operations. It takes me 4 operations to reach this point. Okay, so in this case it works simply by dividing it. But what happens if we have the point 9, 2? So say we start here. Say we start here, 9, 2. Then we would have 1, 7, 2, 5, 2, 3, 2. And then I cannot 3, 2. And then I have 1, 2. 2, 3, 4. So if I have 9, so this first one was for the point 9, 10, 2. But what happens if I have the point 9, 2? Then I calculate again 9 minus 2. This is the difference, 7. I divide it by the smaller value. So how often fits the smaller value into this? It is 3 times. But then I have 1 left. So if I have 1 left, so I can calculate whether I have something left or not by calculating 9 modulo 2. If 9 modulo 2 is larger than 0, this means I have 1 left. So this is a Boolean value. It can be either 1 or it can be 0. So if it is 0, this means that so the larger value modulo the smaller, this means that it fits perfectly. So for example, in this case, 10 modulo 2 is 0. So it fits perfectly. I have 4 operations. So 4 times I have to subtract until they reach a point where the first value is not larger than the second value anymore. So I have like 4 ops, 4 subtractions to reach it. And here I have 3 subtractions to reach it. But 3 is not correct. Actually, I have to reach in 3 operations. I'm at the point, so 9 7 7 9 2. I start with 9 2, then I have 7 2, 5 2, 3 2. So after 3 operations, I'm at point 3 2. But then I can still subtract. I have to subtract 2 from the larger value 3. So I have 1 more operation. So therefore I simply, so the formula is, so say I have the larger value is x, I divide by the smaller value, and then I add the check, I add the result of the operation x modulo 2 is larger than 0. Okay, so this is either 1 or 0, so I add this to the result. Okay, and this is, then I get the number of operations needed to transform this point to the point where to the like the next point where I have to where I have flipped the maximum and the minimums. And in this case, now I have to subtract the x value from the y value. So now the y value is larger. So this gives me a number of operations, and I think this is a good formula to do this. And then of course, I mean this must be integer division here. I want to have an integer, not a float. So I will keep this formula in mind and I will use it in the code. Now I'm getting really exhausted after like 3 hours coding this. Okay. This one was really inefficient, so I hope that my next solution will be more efficient now. Okay. Again, we have our goal. Now we don't need to store anything. So this is now really nice. So now I don't call this goal, I just call it x and y. I start with some x and y. Values. Now I do some calculations. I always have the while true loop, just keeping the placeholder so that I can replace it later with what I want. So I have a while loop. Then I check if x is larger than y. I do something. Else elif y is larger than x, I do something. Else I return impossible. Why is that? Because I mean, if they are the same, then this means that no value is larger than the other one. No, this is not true. This is not the case. 2, 2. So basically here I check if goal and x, y. Okay, so now I still have the goal because I need to check if I have reached the goal. So if the tuple 1 1 is equal to my tuple x y, I return the string value of my current counter. So my counter is initially 0. This means that like in 0 steps I reach the solution. So if my goal is already 1 1, then of course I mean I have 0 steps I reach the solution. And then in each loop iterations. Okay, so now again I have to think about this. Okay, so this is like my first check. Are we done? And now we check if x is larger than y. We need to come up with the next tuple. So basically what we could do now is to have a for loop and to subtract the smaller value y from the larger value x. A lot of time, but actually I just want to use the formula I have created. So we have so we have a new tuple value xy, new tuple value, and now we also have a new counter value. The counter value is how many steps do we add to the counter. So we add at least one step, but maybe more steps if the value y fits multiple times. So if you need to subtract the value y multiple times from the value x. So therefore we calculate x divided by y plus x modulo 2 is larger than 0. So this is a Boolean value. It's either 1 or 0. We have x divided by y, but this is an integer float division, so we need to convert it to an integer. Okay, so this is the number of steps, number of times we need to subtract. So if, for example, so in this example, so let's go here. If we have the value 10, 8, then putting this into my equation will result in 10 divided by 8 is 1. So we use the integer conversion. So 10 divided by 8 is 1. 1 point something, but we convert to an integer, so we have 1 plus 10 modulo 8. There is a remainder, so 10 modulo 8, there is a remainder, so so we add 1. So we get 2 here. And now does this work? So basically yes, so we have one operation. No, actually no, I have done mistake. So I don't have to calculate x divided by y, but x minus y divided by y. Okay, so forget about this formula even. Must be x minus y. So this is the difference between both. And from this difference, we simply we first subtract the y value, the smaller value from the difference. Then again we subtract it, again we subtract it, again we subtract it. So we always subtract the smaller value from the difference. So basically this one, so we have 10 minus 8 is 2. 2 divided by 8 is 0. So we have 0 here. 0, and then we add 1. So therefore we obtain the result 1. Okay, so what happens for other values? Let's check for our formula. Let's check a few maybe. So 10, 8. We have 10, 8. Now let's, what if we have 10, 2 or 10, 10, 3? So if you have 10, 3, we calculate 10 minus 3 is 7. 7 divided by 3 as an integer plus 7 modulo. So this also has to be x minus y modulo. The difference between both, x minus y modulo 2 is larger than 0. So 7 modulo 2 is 1. So 7 modulo 2 is 1. So we have 1 larger than 0, which is the case. So therefore we add 1. And of course this one, 7 divided by 3 is approximately 2. So overall we get 3. So let's check. 10, 3. Next one would be 7, 3. Next one would be 4, 3. Next one would be 1, 3. So we have 1, 2, 3 subtractions. Okay, so this gives us the number of subtractions needed, number of operations to obtain our next tuple, where our larger value is now finally smaller. So this is like the only advantage here compared to subtracting is that we have one operation that calculates this instead of having to subtract multiple times. So therefore, if you have an extreme case like 10, 1, again we calculate 10, 1. So we calculate. So what we would have to do is this 9, 1, 8, 1, and so on until we reach 1, 1. So this would be from 10 to 9 to 8 to 7 to 6 to 5 to 4 to 3 to 2 to 1. So we would have 9 operations. So we want to have 9 as a result. So we map this whole thing. So we calculate 10 minus 1. 10 minus 1 is 9, divided by the smaller value 1, plus 9 modulo 1. Now larger than 0. So in this case 9 modulo 1 is 0. There's no remainder. This is 0. This is 1. So therefore the result is 1 here. So it's 9 here. This is not 1, this is 9. So therefore 9 and 9 both are the same results. Okay, so this helps us in this calculation. Okay, so we want to do this one. So basically x minus y divided by y, and here we also have x minus y modulo 2, and we check whether it's larger 0. Good. So now this is the number of operations needed. And now we need to determine the new tuple. And this can be now easily done by replacing xy with, so x is a larger value, so we have to do x minus let's just call this subtractions, the number of subtractions, num subs. This is the number of subtractions, of subtraction operations, and we simply add this number here. And now we calculate number of subtractions times the smaller value, because each time we subtract the smaller value, so this is like the multiplication. So this gives us the total number of subtractions. So if we subtract, say 2 9 times, then we have subtracted 18. Yeah, so 9 times 2 is 18. So and the smaller value y remains unchanged. And now after this operation is the case, we are now sure that in the next operation value y will be actually larger than value x. And we have simply updated this. And if it is only one operation, then it's only one operation. So I mean, again, in this case where it is 10, 8, we calculate 10 minus 8 is 2. So 2 divided by 8 is 0. And we have so I have to check integer division. So now this will throw an error, but no worries. I just want to try integer division. 10 divided by 3 is 3. Okay, what happens? 11 divided by 3. Okay, so actually this is what I want. So I can also use the integer division operation here. Instead of converting this to an integer, I just use integer division. Okay. Now we do the same. So now if y is larger, then of course everything has reversed roles. Now we calculate y minus x divided by x, and we calculate y minus x modulo 2 if it is to check whether it is larger than 0. Calculate c as num subs, and we have xy. Now x remains unchanged, and we calculate y minus num subs times x. So this is because we subtract the value of x. Okay, and now we do this, and if we land, for example, at 1, 1, then we are done. Okay, and when does this not work? So one case is where both have, so where we land the only case where this doesn't work is if one value is larger than the if both values are are the same, but they are not 1. So we check while so as long as one value is larger, we can subtract the smaller value from it. So we can proceed. And this will only stop. The only problem is that if we are, so while x is not equal y, So if they are equal, we simply skip the loop. But the problem is that if they initially are both 1, then they are equal. So therefore, we want to return impossible here. If x, y equals 1, 1, else, no, basically in this case we want to return string C as impossible. Now we don't even need to do this one, right? Okay, so as long as they are different, if they are equal, so say x is the same as y, and they are both 1, this means that C, our counter, will be 0, and we return our counter if they are both 1. Otherwise, we still know that they are equal. Why do we know this? Because I mean, either we would have left the loop immediately, or we enter the loop. This means that they are different. Now they are different. So they are different. This means that one of them is larger. So if x is larger, then we do something and set x and y to new values. Otherwise, if y is larger, we set x and y to new values. So now they are, again, after leaving this loop, there are now a few cases. Now either they are the same, then we leave the loop, or they are the same, like they can be 2, 2, for example, or 4, 4, or 3, 3. So they can be the same, but not being 1. So if they are the same, but they are not 1, so then this means that we return impossible, because x and y are not 1, 1. So they are the same, but they are not 1, 1. So therefore, it's impossible to solve. Otherwise, if they are different, then of course we stay in the loop until they are the same. And if they are the same, then again, if they are 1, 1, so if they have reached our goal of 1, 1, our starting point basically, then of course we are done. So this solution should work now. Hopefully it will work now. Let's see. 5. Integer division or modulo by 0. Now why do I calculate modulo 2? No, I don't want to calculate modulo 2, but modulo y. No, here I want to calculate modulo y, and here I calculate modulo x. Actually, no, this is not, it's not precise. The problem is that, say they are the same after this computation, so we have 2, 2. For example, say we have 2, 2. This means that we calculate 2 minus something, 2 minus the smaller one, which is, say it's, I know if we have 2, 2, we would not enter this and we would not enter that. So say we have 3, 2. No, I think. Okay, so we have 4, 1. impossible, impossible. So this was actually, so let's have a few more solutions. So 2, 4 is impossible. 2, 2 also should be impossible. Like 10, 10 should be impossible. Why? Because we have to calculate 10 minus 10 is 0 for one of the values, so therefore it is impossible. So we have a few impossible values. Let's add some possible values. Say, I don't know, let's try some. 6 and 14. This also seems to be impossible. 2, 1 is possible. Then some of them, maybe some that are possible. So for example, if we have 3 or say 101. So 101 should be possible, right? Because now we calculate even 102 should be possible, because now we calculate no, maybe we stay with 101. Now we calculate 99, so one step we reach 99, 1, 98, 1, and so on, and so it's possible 99 steps to reach 1, 1. And what happens if this is 2? Then we have 198 in one step, 96 in one step, 94 in one step, and so on. So we have until we reach 2, 2, 2, and then this would be impossible. Okay, so this should be impossible. Okay. So what happens if you have a large number now? Say 10 to the power of 5. So this is now 100,000 elements. This is as large as okay, so it's really fast. So let's have let's make it 10 to the power of 10 for both. Also very fast. Okay, I will have another experiment. Now we do 10 to the power of 100, or say no 50, which is the maximum value. And here we have the string of 1. So we have 10 to the power of 50 and 1. So now this is possible. We simply need to subtract 1 a lot of times. But it would be very slow with the approach we have previously taken, yeah? But because previously we would have started with 1, 1, and then we would have added 1 to the x value, then to the y value. And then we would have explored those two options, and then we would have this whole branch of values. Okay, now execute this. Wow, okay, so it's blazingly fast. It's as fast for large values as it is for small values. So this is just because it's just some basic operations. Okay, so this is a nice value. It works beautifully. It's concise code. It's very efficient. It's short, readable. You have to understand the algorithm, but I mean, I explained it now very in depth. So I hope you understood the idea. So I like this solution. I like this a lot. So let's see how this solution works out. I will copy it. Also copy it into my document. So it's like my third approach. Second solution. So we have now third solution. Okay. Now, should we submit this? So this is not it. This is it. Okay, so we need to define the solution. Let's store it and run some tests. solution.py. All test cases passed. Okay, perfect. So now we can submit the solution. Submit solution.py. Yes. Okay, now they ask me, the code is strong with this one. You can now share your solutions with a Google recruiter. So if I wanted to work at Google, now I could share the solution. If you opt in, Google staffing may reach out to you regarding career opportunities. We will use your information in accordance with our applicant and candidate privacy policy. Yes, no, or ask me later. Okay. To share your progress at any time, use the recruit me command. Okay, so if you wanted to work at Google, so now this is it. You just have to pass level 3 and then you would have the opportunity to work at Google. Okay, thanks for listening to this video and see you in the next one. Bye.